So hello everyone. We saw yesterday how to select features visually. Now we are going to see today how we will do that thing with the help of some measure. So the basic idea was you choose the feature. Say here there are two features such that you get partitions which are pure. Okay. So if I choose this horizontal line, then I get two sections, say 1 and 2, and in section 1 I get pure labels like blue, and in the other section I get say orange. So if I divide the line uh, vertically, if I divide this line vertically, then you will see that if I use x-axis and divide vertically, so what happens is this section consists of blue plus orange, and this section also consists of blue plus orange. So this is not a good idea of division. So better idea is use the horizontal line at proper place so that you will get good division of data into two separate classes. So you can even, as I said, you can even use this vertical line and then further divide this into four sections, and then you can get pure orange and pure blue nodes. So here in first case, if I follow the first procedure, then I will require four leaf nodes for omega 1 and omega 2. So two nodes for say omega 1 and two nodes for say omega 2 here. But if I follow the idea of horizontal split, then I have straight away two nodes for omega 1 and omega 2. Okay, so this the structure becomes simpler when I go with second idea rather than first idea. So it is a critical thing to choose the feature. Choose the feature with whom you will start your journey of division. Okay, so if you by chance choose a feature such that it is creating further children which are still not pure, then you have to struggle a lot. That means you have to create more nodes or more branches for the tree, and you would finally to get the children which are pure. Okay. But if you choose a proper feature, then you can reduce the complexity to a lot extent. And we have seen this example how we can construct actually the nodes, say root node, and then this internal nodes and leaf nodes. Then came the idea of measuring the impurity in your groups. Say, for example, I have this complete data and I have divided this into two halves. Say, complete set is D, but I have divided into two sets, D1 and D2, using some way. Okay. So initially, as a mixture, suppose there are 60% samples of omega 1 and 40% samples of, let us say, omega 2. So this was my initial mixture when I started. So this is the ingredient of data set D. Now when I split this data into two halves, say D1 and D2, so I get some two sections, and say D1 and D2. Now within D1, you may have say 80% omega 1 and maybe 20% omega 2, and in omega second group you may have 90% omega 2 and maybe 10% omega 1. If this is the mixture after division using some feature, then this is a better picture than the D itself. Okay, D consists of 60-40 ratio. When I take D1, it is 80-20. When I take D2, it is 90-10. So if I want to stop my say tree generation, I can declare this as omega 1 and this mixture as omega 2. So there will be 20% error here and 10% error here, but my job is done. Okay, so but the question again remains, how do you achieve this purer and purer form? So the idea is use the measure of impurity. The measure of impurity will guide us to choose a proper uh, feature. So how it is done, that we will see today with one example. So there are that we normally there are three measures that we use. First one is entropy, which was proposed in ID3 algorithm, and the second one is variance, also known as Gini impurity for multi-category, used in CART algorithm, and this is a normal misclassification impurity. So as I said earlier, that entropy is the measure of randomness, how random you are. So when you have more random, so there is no concrete structure, then your entropy is high. So like this, if the distribution of bricks, then there is high amount of uncertainty. So your entropy is high. But when you have order set of bricks, then you have less entropy. So uncertainty more, entropy more. Okay, so you can see here also, if this is the organized way of putting some arrows in a box, then this has less entropy compared to this random distribution of arrows. Now then, we have taken some example about say two classes and 50% class 1 and 50% class 2, like that. So entropy is 1, and then when there is certainty that only omega 1 is present in my distribution and only omega 2 is present in my distribution, then entropy is 0. So as shown here, the entropy is 0 when probability is 0, as well as entropy is 0 when probability is 1. So remember that when you are certain about something to the extent of full, then entropy is 0. Say within this data, there is no data of pen. If I am sure 100%, then entropy is 0. But I know that all the samples in the data space are of pen. That means probability is 1. Then also there is no information. So whenever there is uncertainty, you will find entropy is high. So in a two-class problem, you will see that entropy peaks at probability 50%. In a multi-category, it will be 1 over k. So if there are k classes, then entropy will peak at the probability equal for all the classes k, with probability say of kth class is 1 over k. So I should say pi, so that we will not get confused. Say for ith class, this is equal to 1 over k, provided k is number of classes. Then yesterday we have seen the first step when you are being provided some table like this. So let us revisit that and then we will continue. Now what this example is, this example is a real kind of thing, that is ophthalmal data set, and you have 24 instances here, and the, there are some 4 features and 1 outcome, that is class. So classes, that is omega 1, omega 2, omega 3, they are here. Omega 1 is contact lens, omega 2 is normal glass, omega 3 is nothing. So these are my classes. I could have written like this. But for simplicity, I'm just writing numbers. Then I have, say for age, there are 3 values available: young, middle age, old, and they are encoded with these numbers. So this table is encoded with some numbers and the meanings are given here. Okay. So we are not interested in meanings, we are interested in how to uh, construct a decision tree for this data. Now, first of all, what we do as a first step, step number 1, is to find out entropy of this table. How much information uncertainty involves in this table. So the basic idea is to find out entropy of the complete table. Now, how do I do it? I just count how many samples of, say, 3 classes do exist in this table. So that is my simple way of doing it. So there are 3 classes and 4 samples belong to class 1, 5 samples belongs to class 2, 15 samples belongs to class 3. Okay. So use your entropy formula. So negative probability into log 2 probability. So sum over all the classes. So I can, maybe I can write here. Say j equal to 1 to say k. So p of j log 2 f j. So this is just expansion of that. And so when I say j equal to 1, that means I am talking about class 1. Then there are 4 by 24. The probability is 4 by 24. When I talk about class 2, it is 5 by 24. And class 3 is 15 by 24. So just substitute values accordingly. You will get some number that is the representation of uncertainty in this table. Now we will move on to the actual algorithm called as ID3. So ID3 decision tree induction algorithm was proposed in '86, uh, and the method actually called as interactive dichotomizer. So dichotomizer 3 actually. So the short form is ID3. This is very popular algorithm for construction of decision trees. At each node, the splitting attribute is selected to be most informative amongst the attributes not yet considered in the path starting from the root. So what we do is we start with the root node, we choose a feature which is most informative. Okay. So every time we do splitting of table, then we choose a feature for splitting which is most informative. So I created this root node and then I choose the most informative feature, suppose F1, and then I break this table into two children, and then I suppose use F3 here to break it further, maybe here F5 to break it further, and I keep on doing like this. Every time I use the feature which is not used already. Say F1 was used here, so I will not consider F1 here. Other than F1, whatever is there, that I will try to use. So until I exhaust, then I can use the remaining features. A measure called information gain based on entropy is used here to select feature for splitting. The attribute with largest value of information gain is chosen as the splitting attribute, and it partitions into a number of smaller training sets based on distinct values of attributes. It is observed that splitting on any attribute has the property that average entropy of resulting training subsets will be less than or equal to that of previous training set. Meaning is, if I start with root node and then say this is D, and if I divide into D1, D2, so entropy at the beginning is suppose E, and entropy here after breaking is say E1, E2. So this average entropy at this level is either equal to this or it is less than this E. Okay. So E is less than, E is greater than equal to say E1 plus E2, some average. So this is actually weighted average. I'm just writing for simplicity as plain average. So E1 plus E2 by 2 is always less than or at the most equal to the entropy at the beginning. So we have seen the entropy of the table here as 1.3. So if I start splitting this table into smaller tables, then the entropy of smaller tables will be less than 1.3. So that is what the meaning is. Now, what is the information gain? So let us define few terms before we do the calculation. So here the alpha is called as information gain. D is the training set. Mod of D is the size of training set. ED, that is entropy of the training set, and the entropy of training set is calculated as we have already discussed. Now the information gain calculation requires the probability. So probability for each class you can calculate as number of samples of CI class in D. Just count how many are there. So we'll take example so that this will be more clear. So for each class you count how many samples do exist out of the total number of samples. Suppose we want to partition D on small on some attribute A having m distinct values, A1, A2, AM. That means we have some attribute A and it can take value A1 or it can take value A2 or it can take value A3 and so on up to AM. Okay. AM. Then the attribute A can be considered to split D into M partitions. Okay, so for each value of A, there will be partitioning of table. Suppose I said color is my attribute, and it can take red, green, and blue value. And this is my attribute A. So then this is called A1, A2, and A3. So when I say find the samples with color equal to red, then all the samples with color red, they are separated, then green, then blue. So your table initially is a complete table is now divided into smaller tables based on value of A. Okay, so you will get three sections because your A can take three values. If your A can take m values, then your table will break into, say, number of breakings will be equal to m. Now the weighted entropy for all partitions of D with respect to A is given by, so this is important formula. As I said, there will be a weighted entropy calculation. So weighted entropy means you will calculate the entropy for all these sub tables, let us say E1, E2, and up to EM, and this was original E. So what I do is, after breaking with the help of attribute A, the average entropy for the problem is given by summation, say J equal to 1 to M. Then what I do, I just count how many elements of this D are appearing in this. So elements here are suppose D1, then D1 by number of elements in D1 by number of elements in D multiplied by entropy of that table. So entropy of this table is E1. So I'm writing E1 of D1. So this is entropy of the first box multiplied by its weightage. How much samples, how many samples from the original source it has captured. If more the capturing, more is the importance. Then I can write for D2. So this will be D multiplied by ED2 and till last, this one, last division. So if this is done, then you are doing actually weighted sum of all the entropies in this rect, you can say, table. And this is written in the summation formula. So our objective is to split D using some attribute A and produce an exact classification of the pure. We are trying to find out actually pure and pure sections. And that is all sample belong to one class. So we have to choose some attribute such that when I break the table, we will get pure and pure samples belonging to certain group. However, it is quite likely that the partition is impure, that is, they contain samples from two or more classes. In that sense, the weighted entropy EA D is a measure of impurities, or you can say purities. A lesser value of EAD means more pure partition. So when you go from top node E and you split it into many nodes and you get some entropy here, say ED, and ED is less than E, so ED is less than E, then you have gained some information. Okay, so you have reduced the uncertainty if you are doing like this. So if your partition is able to reduce the uncertainty, then it is good. Okay. So we will keep on reducing the entropy. So the information gain is the difference of the parent node entropy minus the children entropy. Okay, so this is parent entropy E. Then after division, you get some children, and it is EAD is the weighted entropy of them. Then ED minus EAD is the gain. Okay, so when you have positive gain, you will have positive gain when the root node entropy is more than the parent children node. Okay, so we are in search of now such a parameter, such a feature which gives me highest information gain. Okay, so we will choose a feature which will give me highest alpha AD. So that is our technique to choose the feature to break the table. Now let us see our earlier problem. So here for the D, so this is my complete data set D. Entropy was 1.3261. Now, what we can do is we start splitting the table. We are trying to split this table using a feature called age here. Suppose I choose this feature for splitting the table. So splitting on age at root level, it would give three subsets, D1, D2, D3. Why? Because age has three values. So when I say age equal to young, some portion of the samples, say age equal to 1, means these are the samples with value age equal to 1. So they will be declared as subset D1. So this will be first partition of my table. Then you say middle age, that is age equal to middle age. So value is 2. So from this to this, you have now D2. And the third one is old. So this portion is old. So earlier I was having complete table with 24 samples. Now they are split into three sections, D1, D2 and D3. Now the entropy of D1, D2, D3 of the split data sets we need to calculate, and then we find out the corresponding weighted entropy, and then we will see whether this is a suitable choice or not based on the entropies of the other features. So what we have to do basically is we calculate a split entropy for age, then we take eyesight, okay, then estimatic, and then use type, and we calculate EAD, that is E age D, then E eyesight D, that is EAD, that is E use type D. So we will calculate for each feature, if I take this split on each feature, what is the entropy, whether it is more or less, whatever it is. So compared to this E. Now we will choose such a feature which gives me highest information gain. That means which feature is giving me lowest entropy. So the information gain alpha, uh, just 1 second. We'll see how we can do this. So information gain on splitting with age. So age equal to 1, you will get this table. Okay, so there are two samples that belong to class 1. There are two samples belong to class 2, and there are four samples belongs to class 3. So when you take the first portion of your data set, that is based on age equal to 1, D1, you get a split like this, and in that split you have mixture of uh, three classes, that is class 1, class 2, class 3 with 2 to 4 samples. So for this 2 to 4, that is 4 plus 2, 6 plus 2, 8. So in total we have 8 samples. So probability for class 1 is 2 by 8. For probability for class 2 is again 2 by 8. And probability for class 3 is 4 by 8. So use this probability and your entropy formula, substitute the values, you will get entropy for this small table as 0.5. Okay, entropy for this small formula is, I think, 0.5. You verify these figures. Okay, so I think it is 0.5. Age with value 1. Now then take the second portion of the table with age equal to 2. Then you check the mixture. There is again a mixture. How many class 3 samples? So you can see 1, 2, 3, 4, 5 class 3 samples. So probability is 5 by 1, 2, 3, 4, 5, 6, 7, 8. So 5 by 8 is for class 3. For class 2, the probability is 1 here and 1 here. So 2 by 8, probability again 1 by 8. Okay.